Well, hello. So, welcome to our last lesson of this unit, which is going to talk about something we call least squares regression, which is basically the real name for our regression line or regression equation. And then we're also going to look at a little bit of what happens when our data is not super linear or when we have some departures from linearity. So, a couple of things we're going to do today: define and solve for least squares regression equation, differentiate between outliers, influential points, and describe their impact on the regression equation and the correlation coefficient. And then we're also going to recognize and use transform regression equations. Lots of stuff we're going to get into today, so let's get started. All right, so firstly, a little bit of a definition and some facts that are good to know because these like to show up on multiple choice questions a lot. The official name for the regression equation that we write for a line of best fit, right, is a least squares regression line, sometimes shortened to the LSRL. So the least squares regression line. And the reason that it's called this is because it minimizes the sum of the squared residuals. And we'll probably talk a little bit in class, and I'll show you some visual examples of data. But if you remember, a residual is the distance between the point and a line, or a point and the line of best fit. So if we take all those residuals and square them, so square those differences and then add it all together, right? The least squares regression line compared to any other line we could make or line of best fit we could come up with, that least squares regression line is giving us the smallest sum possible of the squared residuals, which basically means that overall our residuals are as small as they can possibly be. Okay. Another thing that is true about this line is that the sum of all the residuals themselves will be 0. So if we square the residuals and add them together, we want a super small number. But if we actually add the residuals together, we should be getting 0. And that basically tells us that the line is going through kind of the average or the midway of all of the points, because the residuals, if I add them together, some are positive, some are negative, is going to equal 0. And then the last thing is that our line of best fit, our least squares regression line, will always go through the point x bar, y bar. This just says xy. It should say x bar, y bar, meaning it goes through the point mean of x, comma, mean of y. So let's look at a little bit of visualization here. So this is our, let's say this is a set of data that we have. This is a scatter plot looking at mother's ages versus father's ages at the time of student's birth. And we want to define a line of best fit. So again, that last fact we looked at said that it always has to go through the point mean of x, mean of y. So the mean average of the mother's ages is like 20, almost 29-ish. The averages of the father's ages is a little over 30. So that point x bar, y bar is a point that our line of best fit has to go through. From there, when we talk about the slope of that line, the slope of that line of best fit is kind of having to do with a couple of things. It has to do with the standard deviation of our y variables and our x variables, because we want the slope to represent the average change in y divided by the average change in x. But it also has to do with r, which is our correlation, because if the points are super spread out, meaning our correlation coefficient is weaker, then that's going to have an impact on what our line of best fit looks like. So that is how we find our slope, by doing r times standard deviation of y divided by standard deviation of x. And then from there, once you kind of know it goes through this point x bar, y bar, and it has that slope, we could obviously work backwards to figure out what the y-intercept is. So let's look at a situation. We know the correlation, we know r, we know the means and standard deviations of both x and y, then we could use that information to come up with an equation for our regression model, for our least squares regression line, by using these formulas. And these formulas are on the formula chart. From here on out, I'll let you use that formula chart for all quizzes and tests that you take. But it's also a formula chart you use on the AP exam. So these formulas are on there. They're not things we have to memorize. So I'm going to kind of show you an example of how we would use those formulas to build a regression, least squares regression equation using this information we're given right here. In this example, I'm just straight up giving you the information, and we're going to go from there. A lot of times it might come up in a word problem and you have to differentiate it. So let's look at that example. So I'm going to start by finding the slope. So again, our slope is equal, or b equals to r times standard deviation of y divided by standard deviation of x. So I'm going to plug in that information to find the slope, which is b, or sometimes it's written as b1, same idea. So r is 0.5 times the standard deviation of y divided by the standard deviation of x. And then I'll do a little bit of simplification here. 3 over 2 is 1.5. And then I'll multiply 0.5 times 1.5 is 0.75. So that is our slope, which is b, or b1. And then from there, I'm basically just going to plug in. So you do get this formula on your formula chart as well. But really, you can just kind of think of it as I'm using my regular equation of the line. I'm going to plug in the mean of y and the mean of x as y and x to figure out what a is. So I'm going to use the mean of y for y, which is 20. A is what I'm trying to figure out. A, or sometimes it's written as b0, either one. Plus b, which we just figured out was 0.75, times x, and I'm using the mean of x as x, so 10. So I'm going to do a little bit of math. And that'll leave me with a equals 12.5. And again, b0 is another, sometimes we see that for a. So once we have those two values, I can now fill in that equation. So y bar, I predicted y, is equal to a plus b times x. And that is my linear regression equation. Usually this problem, if it comes up, it's not a super common problem we see on AP exam. There might be one question using this kind of thing, and it's almost always in a multiple choice question. So you're kind of picking from options. All right, my next little mini topic is we're going to talk a little bit about outliers on a scatter plot, and a couple other vocabulary words that are important in the same conversation. So when we're just dealing with one numerical variable, right, and when we make a histogram, when we make a box plot, an outlier is really just defined as a point that is far away from the rest of the points. When we're talking scatter plots, and we now have two variables that we're interested in, outliers, we need a little bit more vocabulary and a little bit more kind of, it depends on what the variables are. So we're going to look at that, on how it affects things. So we're going to look at that. So if a point's x value is far from the mean of the x values, it is said to have high leverage. So high leverage is one of the terms that we see occasionally. High leverage just means that that point has the potential to change the regression line significantly. A point is considered influential if omitting it, taking it out of the data, would give a very different linear model and possibly also a very different correlation. So I'm going to show you an example on an applet that I like to use. So let's say I have a line or a set of points that looks something like this. All right, so it's got a pretty strong positive correlation. Correlation is 0.8978. Right? If we take a point and kind of drag its x value much higher, right? Its x value has to do with how far left and right that point is on the graph. So if I take this point right here and I move it way over here, right? A couple things we notice is that that line of best fit was very easily affected. It's almost kind of dragged or like magnetized towards this point right here. But also notice that my correlation changed a lot as well. So we went from a correlation that was pretty strong in the 0.9 region to now it's 0.54, just from that one point. So that one point had a pretty big impact in terms of how it affected both the slope of the regression line and how it affected correlation. But let's take that same point. I'm going to put it back kind of where it was. Right? It's about where it was. And let's say I take that same point, but instead of changing its x value, I'm going to change its y value. So notice with this, my regression line changed, though it didn't change a ton. It didn't change as drastically. The slope got a little steeper, but not significantly steeper. And then also look at my correlation coefficient. It went from 0.89 to 0.82, still in the strong range, right? If I move this point further over this way, let's say, actually I'm going to move it back. If I move that point back where it was, And let's say I take a point from the middle and kind of move it up, right? I'm changing its y value, right? My regression line doesn't change a whole lot. Right? My correlation did change a lot on this one, though not as much as it did on some others. So just kind of showing you how it affects that linear regression equation. That linear regression equation is very highly motivated by x value changes, whereas if I'm changing the y value, it doesn't change it nearly as much. Right? The other thing to notice is that if I have a point that might technically be called an outlier, or you might think of it as an outlier, but it's an outlier that fits within the pattern of the rest of the data, it's not going to change anything a whole lot, right? Keeps my regression line pretty much the same from where it was, and if anything, it's making my correlation even stronger. So while we might think of that as an outlier in terms of its x value and its y value, it's strengthening the pattern that exists with the rest of the points. So let's look at some other examples, and really I'll kind of give you a frame of reference as to what you might be asked on a question. So we have a graph here. There's my graph, there's my scatter plot, and the point I am asking about is that point right there. So my question is this an outlier, or is it an influential point, or is it neither? So an outlier, when we're talking about a scatter plot, an outlier really refers to, it's a point that doesn't fit the pattern, but it's a point that's not going to affect our regression model very much at all. It might affect it a little bit, but it's not going to affect it much. So it's an outlier, it's not fitting the pattern, but it's not affecting things too much. It's not influential in terms of how it's changing the regression line. So that point, I would consider an outlier. It's an outlier because it doesn't have high leverage. Again, high leverage means that its x value is far away from the rest of the x values. So this one kind of fits in with the x values. It's just its y value that's off. So it's going to weaken our correlation coefficient. It might change that regression line a little bit, but it's not going to change it drastically. So we'd call it an outlier. So then we have a graph that looks something like this. So again, I have my scatter plot, and the point that I am concerned about is this point over there to the left. So this one, is it an outlier? Is it an influential point? Is it neither? This is one that I would say is an influential point. So because its x value is far away from the rest of the x values, I consider it influential. It has high leverage, which means it has potential to change things drastically. And because it doesn't fit the pattern of the rest of the points, it's going to weaken things. So again, it's going to weaken correlation, and that line of best fit is changing a lot more drastically than it did before. Then we have a situation like this, where I have a scatter plot, and then the point I am concerned about is that one up at the top left. Would I call it an outlier? Would I call it an influential point? Or would I call it neither? So this is one I would say is neither, because even though its x value and its y value are kind of far away from the rest of the points, because its x value is far away, it does have high leverage, but because it's fitting the pattern, it's actually strengthening correlation, and the line of best fit is not really going to change with or without that point. Right? Taking it away is not going to change it, adding it is not going to change it. It's pretty much going to stay the same. So those are kind of one example each of an outlier, an influential point, and one that is really kind of neither. So that's really how we talk about outliers and how it affects things when we're dealing with two variable data. So last but not least, little section of this lesson is what happens, or what can we do if we determined that a linear model is not appropriate. So remember when we talked about residuals in class and the residual plot, in order to determine if a linear model is appropriate, we look at the scatter plot, does it look linear? And then we look at our residual plot to make sure there's not any major pattern. So if we looked at those two things and determined that a linear model is not appropriate because it looks nonlinear in some way or another, there's a couple of things I can do. So we're not going to go too far into this because this is definitely not something that appears a whole lot on AP exam. So I just want to touch base on it so you can kind of be familiar with it in case it does show up. So when data is not linear, one trick statisticians use is to transform the data. Some common transformations, I'll just show you this real quick. This is data that I would say maybe looks maybe quadratic or possibly even cubic. So when we have data that works with like what we call a power model, so it looks quadratic or cubic or even quartic in shape, one trick that we have is to take the log of both the x values and the y values, and that tends to make the points a little bit more linear in shape and allows us to use a linear regression model to make predictions and that kind of stuff. Another example is this graph right here. It's kind of hard to see. The points are green, but this is one that looks a little bit exponential in shape. So if we have a graph that looks somewhat exponential, then the trick we have is to take the log of just the y values. And again, by doing that, transforming the data a little bit, it creates a graph that's a little bit more linear. Okay. So this may come up on a multiple choice question on the AP exam where you were asked, like, what transformation should we make to make this data linear? Possibly. The other thing we're going to look at is how we might make predictions from model or from data that's been transformed or from equations that's been transformed. So here's an example of a multiple choice question. It says an exponential relationship exists between the explanatory variable and the response variable. The common logarithm of each value of the response variable is taken, and the least squares regression line has an equation of log y hat, or log of predicted y, equals 7.3 minus 1.5x, which is closest to the predicted value of the response variable. So we want to figure out what y is when x is 4.8. So obviously I could plug in the x for x, or 4.8 for x, and I could solve that. So 7.3 minus 1.5 times 4.8, and I would get 0.1. But unlike on a regular prediction problem, that's not my answer, because I still have log of y hat equals 0.1, and I'm trying to solve for y. So then I have to pull out my logarithm knowledge, right? And so if you remember, logs have a base. If this is the common logarithm, if there's no base written, it's 10. So the opposite of log is to do an exponent. So I'm going to say 10 to the on both sides. And what that does is it cancels out the log, because 10 to the and log base 10 cancel out, and we're left with y. And then 10 to the 0.1 is 1.26. We round it. So that's our value of y. Right? But this is a multiple choice question, so I do want to give you another option. If you don't really remember your rules for logs, at the very least you could do just some calculations. So it's kind of hard to see because the answer choices are there now, but I have my answer choices. I could do the thing I did on the right side of the equation, where I'm left with log y equals, and then we solved that and it was 0.1. So I know I want it to equal 0.1, so I could just guess and check. Right? It's probably not going to be a, because a says 0.1, but I could check, and I could type in my calculator log 0.1. Well, that's not equal. Negative 1 does not equal 0.1, so we know it's not that. Then I could try the 0.68. So let's log of 0.68, and I get negative 0.17, so that's not it. Then I could keep going, guessing and checking. Eventually I'm going to find that log of 1.26 is equal to about 0.1, so that's my answer. And so I can do a little bit of a guess and check if you don't necessarily remember your log rules. Here's one more example of a question that asks you to do something like that. So it says the relationship between carbon dioxide emissions and fuel efficiency on a car can be modeled by this least squares regression equation, where x is the fuel efficiency in miles per gallon, and y, or y hat, where that's supposed to be, represents the predicted carbon dioxide emissions in grams per mile. What's the closest to the predicted carbon dioxide emissions with a car of this type with fuel efficiency of 20 miles per gallon? So in other words, we're plugging in a 20 for x, and we're trying to solve for y. So same as before, I could go ahead and plug in what I know, which is the x. So 7 minus 0.045 times 20. And then I could go ahead and calculate that. So 7 minus 0.045 times 20 gives me 6.1. So ln of y hat equals 6.1. And then to actually solve that equation, you have to remember that ln is natural log, and its base is the number e. So to get rid of it, I need to do e to the. That cancels out, so I'm left with just y. And then e is found by doing second ln on your calculator. So e to the 6.1 gives me my answer. So 445.8 or 446 if I round it. Again, just like before, we have answer choices. So if at the very least you could have ln y equals 6.1, and then just keep plugging in values of y until we get that equation to equal each other, which you're going to get C. So that is how we can solve and find predictions for equations that have been transformed in some way. So that is it for today, y'all, for this lesson. I'll see y'all in class next time.